Hello everyone, welcome to lecture 55. So we will continue upon the spectroscopy that we have broached upon, and then we are actually looking at how spectroscopy is a very important tool to look at various sort of properties and understand the dynamics inside a material, how it relates to these properties, right. So we said, okay, so just electronically speaking, a material is nothing but a bunch of electrons arranged in their respective band structure, right. So in various bands, right. And then so we said, so far the sort of energies that we have used, right. So you can excite these electrons either to virtual states or to the real states by using an incident radiation, and this incident radiation can be generated through electrical signals, right, up to gigahertz, or above gigahertz or above terahertz, these are optical signals, right. So you incident this electrical signal on the material, right. So that can be either through probes, either through electrical contacts, or just optically shining light, right. So both of them work. Everything is an electromagnetic wave, right, and you start giving off the energy from the incident photon or incident electrical signal into the electrons, right. So depending on how much energy you are giving and what sort of excitations, electronic excitations you are making, so you are measuring either the virtual properties, either excitations to virtual states or excitations to real states. Excitation to virtual states give you the real part or the scattering part of your refractive index or dielectric constant, and excitations to real states give you the absorption part or the imaginary part of your refractive index or again dielectric constant. These are related, we said that these are related to each other. Okay. So in some sense we are actually looking at the electron dynamics, right. We invoked impedance spectroscopy, and impedance spectroscopy works up to is completely electrical in nature, and it works up to a gigahertz, right. So I showed you how making gigahertz measurements is quite tricky. But you can get so by doing impedance spectroscopy you can get both the imaginary part of dielectric constant and the real part of dielectric constant together, right. So that is your small signal measurement that some of you may have done already in your labs. So where you get the C and the G, C for capacitance, G for the conductance, right. And then you up the frequency a bit, right. So you go to something like 1 milli electron volts to about 100 milli electron volts. You have the so called terahertz spectroscopy to understand the ionic resonances, the bond resonances, right. So and bonding resonances, although they are related to the valence band, the electrons in the valence band trying to contribute to these bond resonances. You can also look at this as an identical problem, as a similar problem in the phonon space, right. So these vibrations themselves you can normalize them, and then you can make phonon modes out of these vibrations, and you can see that these are actually excitations of phonons, right. So phonon energies change, right. So if a phonon can go to a real energy state, then there is absorption of light energy, but if phonon cannot be excited to a real energy state, rather it is excited to a virtual energy state, then there is just scattering, right. So we have seen how Raman scattering versus Raman absorption processes take place, right. So this is the crux of Raman spectroscopy, where you have scattering processes as well as absorption processes in the phonon energy scales, which is about 10 to 100 MeV, and so we discussed what absorption spectroscopy is from the perspective of Raman spectroscopy. Okay. So now so then we moved on, and then we said, okay, so this is up to 100 MeV, but then if you increase the energies further, you are looking now at interband transitions, events such as interband transitions, and that is where optical spectroscopy tools play a role, right. So now before going into optical spectroscopy, let me give you another example, right. So I have again conduction band and valence band. Still we are in conduction band and valence band, we are not yet, these are all the electronic and optical processes happen at the conduction band and valence bands, right. So we have not yet gone inside into the core levels, right. So these are still what are called the valence levels. Okay. Now let us assume that my material has a defect state, or in which an electron can exist. So this is a defect state, it is there in what is called these are deep trap states. Okay. And so if I excite an electron from this state to this state, there are 2 states, let us assume there are 2 states, and then de-excite it, these 2 are real states, let us say, and this energy, right, is in gigahertz, or so is gigahertz is again few 0.1 milli electron volts or something like that. So, this energy is in 2.8 gigahertz. Okay. So, essentially these defect transitions between defect states. So, these are if I have a material, right. So, if I have a material like carbon, right. So, carbon has a certain lattice, right. So, this is carbon or diamond in some sense, right. So, what is the structure of diamond? The structure of diamond is diamond cubic structure, right, and this diamond cubic structure, the perfect structure will give rise to a conduction band, it will give rise to a valence band, there is huge band gap, I think of more than 6 electron volts, right. So, diamond is a very good insulator, and so instead of certain carbon atoms, right. So, this is a perfect diamond, right. So, in blue is perfect diamond, right. Now, in perfect diamond I am going to introduce a vacancy, which means I am going to remove this carbon, right. So, this carbon is gone, but at the same time I am going to introduce a nitrogen, right. So, instead of carbon, one of the diamonds gets one of the carbon atoms gets replaced by nitrogen, right. So, the pink one is nitrogen, and if there is nothing, that is a vacancy, right. So, this is in diamond lattice I am putting in a defect, right, and this defect is what is called an NV defect, right. So, N for nitrogen, V for vacancy, NV center or NV defect, right. Now, I ask the question, because now this defect also so there are certain electrons associated with this defect, right. So, what are the energies of these electronic states associated with this defect, right. Now, if electrons are associated with diamond, they have no density of states in the band gap. Electrons associated with just pristine diamond or pure diamond have 0 density of states, right, in the band gap. So, I cannot find an electron in diamond which has these energies, right. So, energy between this and this level, right. So, there are going to be no electrons between the conduction band and valence band. Okay. However, when I put in an NV center, however, can introduce defect states, right, in the band gap, right, and depending on the charge of the NV center, right. So, NV minus, right. So, if this nitrogen and vacancy can have a charge associated with it, it is not neutral, it is not charge neutral, but this can have a charge associated with it. I can create a couple of defect states, right. So, I am not going into details of these defect states, that also depends on the spin of the electrons, but of the electrons that are sitting in these defects, right. So, these electrons, right, so which are in the band gap actually are localized to the NV center, right. So, they do not belong to the rest of the diamond crystal, but they are localized to the NV center, right. Now, if I look at the energy gap between this, right. So, these 2 levels, it is a 2 level system. I have created using an NV defect, I have created a 2 level system, right. So, if I have created a 2 level system, electron can either be in one level or the other level. So, I have a 2 level system and the difference between these 2 levels is about 2.8 gigahertz, right. So, in frequency, very small teeny tiny separation, right. So, this is in microwave frequency range of 2.8 gigahertz. I have a 2 level system, created a 2 level system. Okay. Now, if I need to know can I excite an electron from here to here, I need to give a 2.8 gigahertz pulse microwave frequency, and then I can excite an electron from this state to that state, right, and then I can again de-excite it, and then again I can excite it and de-excite it, and so on and so forth. So this is a real absorption process that happens, and such two level systems, and these electrons are sort of isolated, they do not have anything else to interact with, right. So they have phonons of course, but they do not have other electrons to interact with, they are sort of inside the band gap, very deep inside the band gap. So it is as if I created a two level system in vacuum, right. So these two level systems are important to create qubits. So essentially so if I am just wearing the hat of someone who knows a bit of quantum mechanics, right. So I have a wave function of electron in this state which is psi 1, I have a wave function of electron in this state psi 2, and I can have electrons either in psi 1 or psi 2. So I am actually creating a qubit which is a superposition of psi 1 and psi 2, right. So my electron wave function will be some sort of a superposition of psi 1 and psi 2, right, and this is nothing but a qubit, and these qubits are very important for quantum computing, right. So qubits are essential ingredients for quantum computing. Right. I can also sense, right. So this energy level of 2.8 gigahertz, right, this is very much sensitive to temperature, right. So in NV centers it is very much sensitive to magnetic fields, right. So by applying magnetic field I will have I will have some sort of a splitting here, right. So similarly by applying temperature I will have some sort of a shift of this 2.8 gigahertz, right. So it is very sensitive to the temperature, the magnetic field, etc. So these NV centers in diamond are very good sensors of temperature and magnetic field, right. So I can make all these devices, right. So I can make a good sensor, I can make a qubit, right. So and magnetic fields, also strain, right. So and strain, right. So everything will change this energy spacing between these two these two levels, and so you can detect it through microwave spectroscopy, and you can say that all right, so my temperature inside the device is actually increased by 5 degrees or 2 degrees, right. So there is very good sensitivity for temperature, and there is very good sensitivity for magnetic fields, and also strain, right. So you can use them as sensors, right. So just by increasing the temperature, the gaps, or so it is more complicated, but these numbers change, it is no longer going to be 2.8 gigahertz, okay. So you can use that, so you can measure it, and then you can use that to calibrate back what is the temperature, what is the surrounding temperature of the sample or surrounding magnetic field in the sample, right. So it is a good magnetometer or a thermometer. Okay. So these are some of the technological outlook of what can you do with such defects. It's not just that so you have spectroscopy and you are studying the properties with microwave spectroscopy, but you can also study the properties and use these materials themselves as some sort of sensors, or you can make devices that can detect electric fields, that can detect magnetic fields, that can detect stress, strain, etc. Okay. On the other hand, you can this is a fundamental unit, this can be used as a fundamental unit of quantum computation, which is called qubit, right. So I have a two level system there which is sort of isolated from the rest of the surroundings, it is smack in the middle of the band gap. So it is not really interacting, right. So if I have a qubit there, that qubit is not really interacting with its surroundings and sort of dephasing or decohering. So I can create robust qubits from two level systems that are such isolated from the surroundings, okay. So NV centers, you can create qubits and do quantum computing, or you can make them as sensors and then measure magnetic fields, temperatures, etc., right. So these are the advantages of doing microwave spectroscopy, not just to understand properties of materials, but you can build more technologically important devices based on that, okay. Okay, so with that let us come to the energy scales now of so we are still from 1 eV or 0.1 eV to about 10 eV, let us say. So, what are the processes that happen from 0.1 eV to 10 eV? We said one of the process that happens is conduction band. I have a valence band, I can excite an electron from valence band to conduction band, right, and I can shine light h nu, I can excite an electron from conduction band to valence band, right, and then that photon will lose some energy. So, I am going to detect a photon of energy h nu minus nu naught, right, h nu 1, that is how we wrote it. This is like Raman absorption, but here I am shining light which is h nu is greater than the band gap, right, and this light energy is so depending on the band gap of the materials, right. So, it is 0.1 eV to 10 eV, right. Okay. So, I can do absorption spectroscopy, and this absorption spectroscopy is either IR or UV or IR or visible or UV, right, depending on the material. If I give you diamond, I cannot do visible absorption, I should do UV absorption, right. So, diamond has a band gap of, diamond band gap is what I said about 6 electron volts, right. So, I have to go to UV excitation to do absorption spectroscopy, right. Whereas if I have something like silicon so will absorb h nu greater than 1.1 eV, right. So, 1.1 eV is the band gap of silicon. If I have something like germanium, I need h nu of greater than 0.6 eV. So, these things come under IR absorption, right. If I have something like cadmium sulphide or cadmium selenide or these sort of optical materials, right. So, or zinc sulphide, right. So, here h nu should be in the visible range. So, these are about 2.2 electron volts is what I said. So, that is visible absorption, right. So, what is a technique that I can use to determine the band gaps of materials? I can use UV-Vis, right. So, which also means IR absorption spectroscopy, right. So, then I can scan the frequencies, right, as a function of the intensity of light that comes out, right. So, I am actually measuring the photon that comes out, the intensity of the photon that comes out, right, and at whichever wavelengths there is some absorption, there is going to be a dip, right. So, let us say this is so there is a dip here and this is going to be something like my band gap, okay. So, I can do UV-Vis-IR absorption spectroscopy. So, essentially I am, or I can plot, instead of plotting intensity, I can plot what is called absorption itself as a function of omega, right. So, in some sense I am plotting the imaginary part of refractive index as a function of omega, right, and this omega will be so I can increase the range of omega. So, typically this is going to be something like or omega or lambda is the frequency is the wavelength, right. So, omega equal to c by lambda, 2 pi omega is this, right. So, c by lambda. So, I can change the wavelength from something like the current day equipments. I can go from 300 electron 1.1 300 nanometers to all the way up to about if I remember it correctly 2500 nanometers or something. So, this is IR, right. So, mid IR, this is UV, okay. So, and then I can get the entire absorption spectrum wherever there is a band gap, right. So, the absorption so essentially if I am going to predict it, right. So, my band gap is somewhere here, let us say. So, this wavelength corresponds to my band gap. So, below the band gap my absorption will be a lot, right. At about the band gap my absorption will reduce, right, and above the band gap I will not have any absorption because of the band gap. So, this is just interband transitions, right. and then so this is how the absorption spectra look like, right. So, and then you can do what are called tau plots and estimate what the band gaps are and things like that. But so in general this is the philosophy. Okay. So, this is UV-Vis-IR absorption spectroscopy. Now, something else can happen, right. So, okay, now let us say I shine light h nu, right, and then I excite an electron from valence band to conduction band, right. So, so this is, and so I am creating what is called an electron hole pair, at least transiently. If I excite an electron from valence band to conduction band, I am creating an electron and hole pair, and this electron and hole pair are also interacting. There is going to be some binding energy between them, with binding energy. Right. So, this is a positively charged particle, this is a negatively charged particle, they bind with each other, and this particle is what is called an exciton, right. So, the exciton, if I have to say how do I creating an exciton, I should give h nu, which is a new band gap, plus the binding energy of the exciton, right. If I give this much of energy, right, some of it is just used to create the exciton and some of it is used to bound the exciton together, right. So, this is how I create the exciton, or this is the energy that is spent in creating the exciton, or the formation energy of the exciton. Okay. Anyway, so I have an exciton, which means my system is in an excited state, right. So, once I have created this, right. So, once the electronic transition has happened, electron transitioned from valence band to conduction band, right, the transition has happened, system is in excited state. Okay. Now, systems are in excited state only for a limited amount of time, right. So, some picoseconds, nanoseconds, whatever it is, right. So, it is in an excited state, this system is in excited state only for a limited amount of time, right. After certain time, the system de-excites. Okay. Once the system de-excites, then what happens, right. So, I have band gap Eg, I have created an electron, an excited electron is here, hole is here. So, this is the excited electron, this is the hole, right. So, now the electron and hole pair will combine, the exciton will vanish, right. But when electron comes back, right, so in the de-excitation process, this emits an energy h nu band gap, right. Actually, okay, let us put it this way. So, when I excite, right. So, let us talk about the excitation process. Let me clarify this because there can be more questions here. So, okay, so when I am exciting, I am creating, so I am giving an energy which is this much, right. So, h nu is greater than h nu band gap. So, as a result, I create an electron hole pair, that is okay. Sorry, this is the electron, this is the hole, and then the so once they create an exciton, the rest of the energy, right. So, h nu will be h nu band gap plus so if I am creating an electron hole pair, the rest of the energy is used to bind the electron and hole, and that creates an exciton. So, I create an exciton, right. Now, when I destroy this exciton, right, or so if it is a direct band gap material, there are these details, right. So, if it is an indirect band gap material, this energy goes off to phonons, right, but it does not matter. But when I de-excite it, so the de-excitation happens from the bottom of the conduction band to the top of the valence band, right. So, the de-excitation happens when these electrons somehow, even if they are at a higher energy, they have to lose their energy and come to the bottom of the conduction band, and here holes so can have a higher energy, they can be somewhere here, but they have to come to the top of the valence band and then emit some light, and that light will have a an energy of h nu band gap, right. So, I can excite with 400 nanometer light, but I can emit at the band gap. Band gap can be some 532 nanometers, right. So, lambda band gap equal to 532 nanometers, right. That's okay, right. So, that sort of a thing always happens. Okay. Now, this emission that is happening at 532 nanometers is what is called fluorescence. Okay. So, we have seen fluorescent materials, right. So, throughout our lives you shine light on a phosphor screen, right. So, the phosphor screen, and you have to shine not any light, but you have to shine only blue light or light that has a lower wavelength than the green phosphor screen, right. So, the phosphor screen appears green, but for it to illuminate you have to shine light which is at a lower wavelength or higher frequency or higher energy than the green light, right, and then it turns green, right. But if I shine red light, nothing will happen to the phosphor screen, right. So, the phosphor screen fluoresces, or this sort of a technique, and if it is fluorescing, the energy at which it is fluorescing is nothing but the band gap, right, in a direct band gap material, of course, in a material that fluoresces well, right. So, this is a technique that is used to determine the band gaps of materials of so I can determine the band gaps of, for completeness I will write direct band gap materials, okay, and this technique is called fluorescence or photoluminescence, right. So, photo for light, luminous meaning the material itself is emitting light, it gets excited to an excited state and the de-excitation emits a photon, right. So, photoluminescence spectroscopy. And what are we doing here? We are looking at the de-excitation, right. So, in absorption spectroscopy we shone light, right. So, absorption PL, right. So, PL for photoluminescence, shine light, shine photon, measure energy loss in the same photon. Okay. In the process you have excitation of the material, you have excited the material and you are actually measuring the excited states of the material. Whereas in photoluminescence I shine photon and I detect another photon that is coming from the material, not the same photon, right. So, I am not detecting the energy of the same photon, I am detecting another photon that is emitted from the material, and how is this another photon emitted? This is emitted, the photon emission happens during de-excitation, right. So, what I am measuring is the process of excitation to de-excitation, right. So, how is the material de-exciting? Right, from a higher energy state, that is what you are measuring using photoluminescence. Okay. So, so slightly different techniques, this is emission spectroscopy, this is absorption spectroscopy, this is absorption, this is UV-Vis-IR absorption spectroscopy. So, that is the difference, both of them can give you information about the band gaps, but so in one you shine light and then you just detect the loss of energy in the same light, right. So, how much of that light is absorbed and used to excite the system, you do not care about de-excitation. In the second one you shine light, you let the system de-excite and then you measure the other photon that comes out of light, that comes out of a material, right. So, that is called emission spectroscopy, and PL is an emission spectroscopy and you can measure band gaps, right. So, using PL. The basic use of doing PL is to measure band gaps of materials. Okay. Now, if we let us further up the game, let us go up to now something like 20 eV and higher, or 10 eV and higher. If we go to 10 eV and higher, we have to use UV excitation. And so one of the processes that happens at about 20 eV is so I have electrons in the valence band, right. This is conduction band. So the bonding electrons, so I have a UV excitation, right. So I give a UV wave, right. So this is electric field is oscillating with time, right. So the bonding electrons, which are polarizations, right. So they these electrons also start oscillating with respect to as a whole, right. So the bonding electrons as a whole meaning as a plasma, start oscillating with respect to the incident light, right, and that is called a plasmon or a bulk plasmon. In other words, I have if I have some free electrons, right. So I have just some free electrons and I apply an electric field to these free electrons will slosh, right. So they will go this way, that way, but they do it completely as a coherent phenomenon, right. So all these free electrons slosh this way, that way, this way, that way, and so on and so forth, right. And then they emit this sort of an excitation is called a plasma excitation or a plasmon. Okay, so if you quantize it, it's called plasmon, right. Now the plasmon, so the electrons in conduction band are freer than the electrons in the valence band, right. So if electrons in conduction band can do this even at visible light frequencies, right. So even at very so at 500 nanometers or even less than that, the electrons in the conduction band can do this sloshing and oscillation. You come to the electrons in valence band, they are heavier, right. So they are more stuck to the nucleus. So to oscillate them, you need more energy, and those energies are in the time scale are in the energy scale of about 20 electron volts. And so then you start measuring the what are called the plasmon oscillations, right. So your incident energy from the UV radiation is being absorbed by the plasma oscillation, right. So the plasma is set into oscillation, and that needs energy from the external source, that is the UV source. Okay. Now all these processes, right. So starting from just the valence the electrons in the conduction band or valence band just jumping 100 nano electron volts and conducting, right, or just oscillating 100 nano electron volts to the virtual state, to electrons in the valence band sort of sloshing at 20 electron volts, right. All these processes contribute to your absorption spectrum, right. So all these processes contribute to how your epsilon changes with the the frequency. Okay. Now I can further go higher in energy scale, right. So so if I use energy scales in the order of something like 100 eV to whatever 8000 eV or 10,000 eV, right, 10 kV, then so now I have gone, I will go deeper, right. So I have, sorry, let me draw it here. So I have a conduction band, I have a valence band, I have other core levels, right. So for me to excite, these are all core levels. Okay. So plasmon or plasma oscillation, right. So for me to excite an electron from the core level to one of these empty states in the conduction band, that takes so that is in this energy range. Okay. So now I am actually doing what is called core level spectroscopy. Okay. And if I have to give energies of 100 eV to 10,000 eV, I have to go towards X-rays, soft X-rays and hard X-rays, right. So I have to use X-rays or high energy electrons. High energy electrons are they also have similar wavelengths as X-rays, about 100 to 300 kV of electrons, right. So, these are electron sources, right. So, this is what is called electron spectroscopy, this is what is called X-ray spectroscopy, right. So, but these are all core level spectroscopy. So, where I excite an electron from a core level to a conduction band and then I measure how much is the excitation energy, right. Now, okay. Now, let me give you a couple of examples. Now, let me say titanium. So, I have a material which is which has titanium in its 3 plus oxidation state and titanium which is in its 4 plus oxidation state. Okay. So, first of all, right. So, my valence band so titanium 3 plus is 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, but I have a 3d1 here. So, my d orbital has 1 electron per atom, right. In titanium 4 plus I have 1s2, 2s2, 2p6, 3s2, 3p6, 3d0, right. So, from if I form a band out of all these titanium atoms, this band is empty. Here I have some sort of a half filled band, not half filled, slightly filled band. Here I have an empty band, right. Now, I am exciting an electron from the 2p state of titanium, right. Here also I have a 2p state of titanium. So, for me to excite an electron, I need this much amount of energy, right. So, this is an empty state. So, I have to be able to excite it to an empty state. So, I just need this much amount of energy. So, this is the h nu I need, right. But for me to excite an electron to Ti 3 plus, I need to excite it to this state because this is already filled, right. So, I need to excite it to this state here. So, I need this much amount of energy. This is h nu, let me call it nu 2, this is h nu 1. H nu 1 is greater than h nu 2, right. So, so looking at the absorption, so I can shine an X-ray and then I can see where the absorption starts, right. So, if the absorption does not happen at h nu 2, rather it happens only from h nu 1 onwards, right. So, it can also get excited to higher energy states, right. So, I will have a band, right. So, I actually I can map the density of states of the empty orbitals, right. So, I can map the density of states of the empty orbitals, empty bands, correct. So, here the density of states is 0, right. So, there is going to be no excitation to these states, but there is going to be excitation to these states, and so if a state can take an electron, it will take an electron, right. So, how many how many electrons can certain states take, that is given by the density of states. So, I can actually map the density of states of empty bands, right. So, using this technique, and this technique is called X-ray absorption spectroscopy. Right. Or the electron analog of it is called electron energy loss spectroscopy. So, this is an absorption technique again, where I shine in this time really high energy X-rays or high energy electrons, and I measure the same X-ray photon or same electron which has a lesser frequency, right. So, which has a frequency of so which has something that gotten absorbed, right. So, h nu so I use nu 1 and nu 2 here. So, let me use h nu and nu naught or something like that. So, I have this nu minus nu naught is the absorbed energy, and if I plot absorbed energy as a function of the nu itself, right. So, here the absorption will start from nu 1 onwards, right. So, sorry, nu 2 okay, nu 1 onwards, and then it will continue to the so to map the density of these states, it will go up to something like this frequency, right, and then the absorption will go down again. But so this is in case 1. In case 2, right, so this is case 1 is Ti 3 plus, whereas in case 2 so the absorption will start a bit earlier, right, and then I end up mapping everything, right. So, this will be Ti 4 plus, right. So, it is not just that so, and this energy, right. So, this the range of these energies, right. So, this will already be fingerprinting the range of this energy will fingerprint that I have titanium in my material, but not just, it is not just telling me that I have titanium, it is also telling me that I have titanium 3 plus or 4 plus, right. So, I can exactly using this core level absorption spectroscopy where I create what is called a core hole and excite this to the valence band, right. So, this is the core hole and this electron is excited to the valence band or the empty state in valence or conduction band. I can actually I can actually understand the chemistry of materials. Okay. So, so this is the advantage of doing absorption spectroscopy at X-ray wavelengths or at electron wavelengths. Okay. So, now let me quickly show you this and then end here. So, for example, here we do this with electrons, electron energy loss spectroscopy, right. Now, so I can do electron microscopy and I can look at atoms, right. So, I am looking at atoms in this material and these atoms, so this is terbium, manganese and oxygen, right. So, if I zoom it up a bit, okay. So, you see that these whiter atoms are terbiums, right. So, the most white atom is terbium and so yeah, so it's here, right. So these the green one should be terbium, yeah. So, and the red one should be manganese. So, the green one, so these big atoms are terbium atoms and in between these 4 terbium squares there will be manganese. I think if you look carefully you can see it, right. So, there is a small manganese dot in between. So, there are 4 terbium atoms like this and in between there is a small manganese dot. Okay. Okay. And then there is something, there is some sort of a defect here, right, and in this defect you see that you see some other contrast, right. So, how do I know that this atom that I am seeing is really terbium, right? I can do this spectroscopy and then I can actually image all these green things, right. So, this is the signal coming from terbium atoms, right. So, I can say that this atom is actually terbium. Okay. Now, in between, right, so somewhere here that gives me these red signals, right. So, the signals for manganese, right. So, I can say that okay, so these in between atoms are really manganese because there is no terbium signal from here, rather there is a manganese signal, right. Now, I can do the same thing for defects and then I can show that so the defects are more manganese rich in this case, right. So, these are all terbiums, this is manganese, right. So ideally outside the defect the structure should be 4 terbium atoms with 1 manganese inside. Inside the defect the structure is going to be 4 manganese atoms with another manganese in between, right. So, you can get such precise details, right. So, by doing such precise chemical details by doing spectroscopy at even higher energy scales. Okay. So, let us conclude this class at this point where so I have taken you from the top of the valence band or top of the conduction band and techniques that are used to detect the electronic properties, what are the so called electronic properties, that where the electronic excitations are just happening at the top of the conduction band or top of the valence band, to we went a bit deeper, we went to milli electron volts, electron volts, looked at the optical transitions, right. So, everything is dynamics, right. So, there is so much of dynamics happening inside the material, you are exciting and de-exciting the material by shining light at a certain frequency. Then I have gone further into exciting the core electrons. So, the first so if you are just exciting the valence electrons or the conduction band electrons, right. So, that gives you just exciting the conduction band electrons and in energy scales which are less than 0.1 MeV, that is just transport measurements, right. So, those are impedance spectroscopy or transport measurements. You go a bit deeper, right. So, you do vibrational spectroscopy or Raman spectroscopy, the Brillouin spectroscopy and so on and so forth, where bonds start vibrating, right. So, these are in those energy scales, right. So, the ionic resonances etc., right. Then you go much deeper right. So then you are looking at conduction band to valence band transitions, you are looking at the band gaps of materials, right. So these are optical excitations or optical spectroscopic techniques, and also the bulk plasmon oscillations and so on and so forth. All these processes happen inside any material, right. And then you go further deeper, right. So into the core levels, right. So then you excite the core levels into the conduction band, then you have you understand the chemistry of the materials. Now I don't care about properties anymore. Now I am looking at actually what is the chemistry, right. So did I get the material that I am making, right. So I am beyond the realm of looking at properties for the entire material, right. So I don't care, I don't talk about refractive index anymore of material in the X-ray wavelengths and so on and so forth. Okay. So tomorrow we will have our last class in which we will actually conclude this spectroscopy. I will show you the analog of core level absorption spectroscopy, the emission spectroscopy, which is called energy dispersive X-ray spectroscopy. But we will talk about that, and then we will end the course by just summarizing everything that we have done, right. So I'll try to show that these dynamics that you are studying here is actually responsible for all the properties, right. So now if you want to control the properties, right, you may want to control the dynamics, right, and how do you control the dynamics is so that's why people do research, right. So in this field, okay. So let's again meet in the next class, and until then, goodbye.